I'm just going to review what we talked about last time. So we talked about what a Grosvenor basis was, and we talked about the initial ideal, right? So the initial ideal is you take the leading monomial of each of the or leading term. It doesn't matter because it's a field. The leading term of everything in your ideal, and you make an ideal out of that. That's a special ideal called a monomial ideal. And a Grosvenor basis is a basis such that the generators for G1 through GR are generators for the the initials of the basis is a basis for the initial ideal. So that's a special condition. And then we gave some conditions about how to compute with Grosvenor bases, right? And what they're useful for. The main thing that they can do is they can solve this ideal membership problem. So we saw this example before where if, that polynomial with division with respect to different term orderings can lead to different answers, right? And also if you permute the things that you're dividing by in the division algorithm, that can lead to a different answer in general. But if you have a Grosvenor basis for a term ordering, then the remainder is always well defined, and you have that something's a member of the ideal if and only if its remainder modulo the Grosvenor basis is 0. Okay. All right. So it makes it so the division algorithm is nice. And so how do you find a Grosvenor basis?
Well, can I ask a quick question?
Yeah.
In the homework, we're finding the Kroll dimension of the C, the polynomial ring over C. Is Grosvenor basis used for that at all?
No, not at all. That has nothing to do with it. That has nothing to do with this.
Okay.
Yeah. So all you have to do there is just find a chain of ideals. And I think I only asked for one inequality.
Okay, you're just adjoining
bound,
indeterminates, right?
And the upper bound, putting an upper bound on the Kroll dimensions is a hard thing to do.
Okay. You're just adjoining indeterminates to make bigger ideals, probably, right?
Yeah.
Okay.
Yeah. Okay. So, all right. So back to this. So we were talking about how you find a Grosvenor basis, and the way to do that is via Buchberger's criterion and Buchberger's algorithm, and they're both really have to do with these syzygy things, right? And so syzygies are where you kind of match the leading terms of two polynomials, right? So that they cancel each other out. So you multiply, you find essentially the least common multiple of the leading terms, and then you cancel them out. And so we did an example here. And again, syzygies depend on a term order. So all of this, every time, if you change the term order, the results are going to change. Okay, so here's the syzygy that we computed, and this was going to feed into a later computation. Okay, and here's the algorithm, or the criteria. The criteria, Buchberger's criteria, was that that if you take the syzygy, so if you have a basis, right, it's a Grosvenor basis if and only if all the syzygies have remainder 0 with respect to that, with respect to this tuple here. Okay, and then Buchberger's algorithm says essentially, okay, if you don't have remainder 0, right, with respect to one of these, you just throw it in, right, and you just keep throwing them in until you have a Grosvenor basis. Okay, so it could be the case that the remainder modulo your tuple here is not going to be 0. So then you just take a syzygy, and then if that is not in there, then you add it into the basis. Okay. So yeah, and this is kind of the process that I said here, is that you just essentially keep adding things here. Okay. So now we went back to this example about ideal membership. So here in our previous computation, right, with respect to the same term order where z is bigger than y is bigger than x, right? So we have that this basis that right here where z, this should be y here. That should be y minus x squared. So this will be a Grosvenor basis if and only if the syzygy is 0, if the remainder modulo this g is 0. And so we did the division and we found that it was 0. So that proved that this was a Grosvenor basis with respect to the ordering. So this is for the ordering z bigger than y, bigger than x. Okay. Later, we'll show that this is not a Grosvenor basis with respect to the opposite order. So if we did x than y bigger than z. So again, this is all order dependent. Depends on the term order. Okay. Yeah. Okay. So here was this example that I was talking about, is that if you switch the term order, right, you're going to get something different, right? You're going to get what was I going to say? You're going to get yeah, well, you'll find out. So here you get this extra term, xy minus z, and then you have to throw this in, right? So here, if you do the division algorithm with respect to this term order and this basis here, then you'll get that it doesn't divide. And so now you have a remainder, and now you make a new basis for your ideal, a new generating set. And now we have to go on and test these for to see if they're in the ideal. Okay, does that make sense? And then I didn't finish this computation, right? And I think I said we would talk about this next time. And so yeah, so maybe how about I just kind of continue with what's going to happen here. So to kind of give you a flavor, but this computation is really long, and I'm just going to punt to a computer computation eventually. Yeah.
So last time, and I don't think you mentioned it in this overview, we did mention that like this is very subject to this term order, and so like being asked to like compute a Grosvenor basis or something like that, if we're not given whatever term order
you got to pick one,
then like we're almost in this like, is there, or just by doing more of these, we'll become more aware of like a good way to choose a term order that allows us to compute this.
Yeah, there's like a whole theory of like all the possible, I think, Grosvenor bases that you can have for like all the term orders, and that goes into like things related to Spencer's research. These things, Grosvenor fans and stuff. So I think that's beyond the scope, and honestly, I don't understand that.
So in general, we just choose and.
Yeah. So if the computation is going, so the thing is like if the computation is going really long, maybe you want to try something else.
Yeah.
And to be honest, I don't know the answer to your question about how to do, what the best way to proceed is.
Yeah. So, I mean, it's probably just by like.
For me, it's by trial and error.
Yeah. Just do them. Yeah.
But I mean, that's probably not a very good answer, and there's probably a better answer, but I don't know the answer.
Okay. Cool. Yeah.
Okay. So, yeah. All right. So here's what I said last time. So we were in this example here. We were doing x bigger than y bigger than z. So let's just kind of continue with this example. Okay. So let's do. Okay. I'm just going to start a new title for the lecture today. Or did we do a new? Do we do a new slide every time? For each class? I forget.
I think we've done a slide and then, yeah.
Okay. Yeah, let's just do. Okay, so where were we? Okay, so we were in the middle of a computation. Okay, and then what we had was, so here's the example. So we had the term order x bigger than y, bigger than z, and we were computing a Grosvenor basis for, and so let's see. So we're computing a Grosvenor basis for, so this the ideal generated by G1 and G2. and G1 was equal to x cubed minus z, and G2 was equal to x squared minus y, I think, right? And so we found that the syzygy of G1 and G2 was like z minus xy, I believe. Yeah. Or xy minus z, right? So let's do this. Xy minus z, and that the remainder, and so let's say G0 is G1, G2. Okay, and that the remainder of, with respect to G0 of this syzygy, was the syzygy itself. Okay, so we make a new basis. And then we call this G1, which is, G1, G2, and G3, where G3 is now the syzygy. Well, let me be pedantic and call this the remainder here, which is equal to xy minus z. Okay, and now we want to check if this is a Grosvenor basis. Okay, now we check if this is a Grosvenor basis. Okay, and so how do we do that? So we only really need to test, so we need to test SG1, G3 and SG2, G3. Yeah. Okay, because we already have G1, G2, that's G3. And so that one we already know is going to be in there. Okay, so so G1 is so what is G1? X cubed minus z. And then this is xy minus z. So this thing here is, so we need to match this. So this is y, and then this will get an x cubed. All right, and so what is that? Okay, so this is minus yz plus x cubed z. Okay, now we do G2, G3. So this is minus, okay, so now G2, G3. G2 is x squared minus y. And then this one is G3, this is xy minus z. So this one can get a y, and this one can get a single x. And so this is minus y squared plus xz. Okay, so let's just write this in the correct term order. This is x cubed z minus yz, and this is xz minus y squared. Okay, so let's test the first one. Okay, so let's test SG1, G3. Okay, so now so check for my mistakes. I'm terrible at these sort of computations. So, I mean, and I expect this one to go long. So we're just going to go through one iteration here, so you guys can see how this goes. And then I'm going to go to a computer. Okay, so we're going to take the division with remainder, and then we have three things that we divide by. So we have G1, G2, and G3. G1 was x cubed minus z. G2 was x squared minus y, and G3 was xy minus z. Okay, and then we have these guys here. Okay, now we just kind of start to compute. So we already get a match on the first time. First time through, we get a match, right, with here. Okay, and so we get z, And then we get x cubed z minus z squared. Okay, and so this becomes minus yz plus z squared. Okay, and so I guess we don't have any matches anymore. Right? So, okay, so let me just make sure that this is what I got before. G1, G3. Oh, okay, this is G1, G3. Hold on, I got a different answer here. G1, G3. This should be an x squared here. You see? This should be a square. And then that makes this a square. That makes this a square. Okay, and that makes this a square. That makes this a square. Oh no, that makes the first one not a match. Okay, so I messed this computation up. Let me fix this. Okay, so we're doing this. Let me just start over here. Okay, so this is a square actually. So this one doesn't divide. Okay, so we first check this. So we're doing this. This one doesn't work. This one works. Okay, so this is a z. Okay, and then we get this is x squared z minus yz. So this is 0. Okay, so this proves that S of G1, G2 are with respect to G1 of S of G1, G3 is equal to 0. And so let's just check here. So it's saying that Z times G2 is S of G1, G2. Okay, and that makes sense. Well, let me not box that. Let me circle this. Okay, so this is what happens because you multiply this times z g2, you get zx squared minus zy, and that is exactly what we have is zx squared minus zy. Okay. Okay, so we tested the first one. Let's test the next one. S of G2, G3. This was equal to, and we computed what S of G2, G3 is. It's xz minus y squared. Okay. So we do xz minus y squared. So far, we don't have to add anything to the Grosvenor basis, right? G1 is the same thing. So this is x cubed minus z. G2 was x squared minus z. G3 was xy minus z. And then, and now we're testing. So we're almost believing that this is a Grosvenor basis, but now we need to test this last term. And I guess none of them divide, huh? F1, F2, F3. So yeah, so there's no coefficients here ever divide, right? So we check this one, and this doesn't work, this doesn't work, and this doesn't work. None of these divide that, right?
And we don't have the relationship that y is x squared and z is x cubed.
No, we do not.
That's
just
rational.
Polynomials, yeah.
Yeah, sweet, thanks.
We don't get to operate modulo the ideal. Yeah. No. But I guess you could probably, there's probably a way to use this in these computations, but I think that would be a different algorithm. Yeah, so this shows that the remainder, bummer, right? So the remainder with respect to G1 of S of G2, G3, well, this is just, it's the same thing. It's S of, turns out that this is S of G2, G3. Okay, and so now we need to expand the basis. So okay, and so we set G2 to be equal to well, G1, G2, G3, and now G4, where this is the remainder with respect to G1 of G2, G3, which is oh, sorry, of the syzygy of G2, G3. And this is so this is x z minus y squared. Okay, so so now there's quite a bit to check, right? So so now what do we need to check?
Taylor,
Yeah.
is G2 x squared minus y or x squared minus z?
Why?
Okay, thank you. Sorry.
No, that's a good catch. This is the type of mistakes that I make. Okay. So yeah, but this it turns out that this one doesn't change anything, right? Because we're only using the leading coefficient, right? Yeah, but that was a good catch. Yeah. So it still doesn't divide, right? We're only using the leading term, right? And then it doesn't divide. So yeah, so then there's nothing, and so the remainder is there. Okay, and so all right, let me just make sure. Yeah, and that's what I got before. Okay, and so now what do we need to check? Okay, so the next step is now we need to check if this is a Grosvenor basis. Okay, and so how do we do that? So we have to do, so notice like with the other term order that we did previously, we finished in the first iteration, right? So term order matters a lot. Okay, so let's just write them down. Okay, so we G2, G3. Okay, so this is a freebie. This is free. Let me just say which ones are free. So this, or let's say already tested. Okay, so this was already tested, this was already tested, this was already tested, and we have 3 more. So these are the ones that we need to test. Okay, and I forget what happens here. So I didn't finish the computation here, but it gives you the idea of like what needs to be done from here. So you just repeat this process. You take the syzygies, right, and then you test to see if they're in using polynomial division. Okay. But so one thing we could do is we could check to see if this works. So now let me go go to my computer here. And I'll show you how this works in the computer. Okay, so let me. Right. Okay. So you guys, can you see my CoCalc window now? So,
Yep.
So if you go to CoCalc, right, you can make a web page. This is an open source version of Sage Math. Let's see. So Sage is this open source software here for symbolic computing, and what you can do is you can look to see if Sage has functionality for polynomial division. So bases Sage, right? So here they'll have some documentation for how to work with Grosvenor bases, right? And you can read the documentation and how to implement rings and how to talk about ideals, and it'll explain. So you can read through this to see how this works. But I'm going to show you how to do this with a particular example. Okay, start the project, and I can share this with you guys. This this notebook. Okay. So so what you can do is so here's the first computation that we did before, right? So to instantiate a polynomial ring, right? So I'm doing it with Q coefficients. You do it like this, and then you specify a term order, okay? And then you can specify the generators of your ideal, and then you can ask it for a Grosvenor basis. So and it'll end up computing something, and what it'll return is the Grosvenor basis for this ideal. So there it goes. And so this is the first computation we did with respect to so lexicographic order. But you'll notice here that I did something weird, right? So notice that in this here, I actually permuted the x, y's, and z's, right? So I made it so it's going in lexicographic order, but for them that's alphabetical, right? So what I did is I just kind of permuted the variables so that z was, so instead of having x bigger than y bigger than z, I just made it, I replaced the x with the z so that z appeared first. Okay, and then this is what we have here. So if you just replace x and z, you'll get the basis that we had. Okay. There's another thing that you can do is so if I were to do so now notice that I didn't permute the x and the z in this example here, right? And if I compute the Grosvenor basis, I get something much longer. Okay, so we already see some of the terms here, right? I think we had this one, right? I think we just had, I don't think we had this one. Did we have this one yet?
Yeah, that's the one we just got, yeah.
XY minus z squared?
XZ minus y squared.
Oh, yeah, that's the one we just got. Okay, so then I guess we were going to pick up another one. But this is a special type of basis here called, okay, so if you look at Grosvenor basis, so anytime you have these things, so first of all, you can do this thing called tab completion. So if I just tap tab, it'll tell me all the functions that are available for this ideal object. Okay, and so they even have the Grosvenor fan thing. So this is what you were talking about like all possible Grosvenor bases. This sort of thing is there. So there is that sort of stuff is implemented. Anyway, we're not going to go to that. We're going to go to Grosvenor basis. Wait. Okay, Grosvenor basis. Oh, do I press enter? Okay, and then there's something cool that you can do. So if you put a question mark here, right, what'll happen is it'll give you the doc string for this thing, and it explains what this algorithm does, right? So it says a Grosvenor basis for an ideal is a generating set such that the leading monomial of the generators is the leading monomial of the ideal. So that's the definition that we gave for a Grosvenor basis, i.e., blah blah blah. Okay. All right, and then okay, so then it describes what it can do, right? And it'll give some examples right here about how to, and this is probably the most important thing to do. I don't know what Katsura 3 is. I guess it's a special ideal, huh? That this person who wrote the software was probably really interested in. Okay. So here's like, okay. Anyway, so they give some examples here. One thing that it should say is that it'll compute a minimal. Where does it say? Okay, so what it does is it computes a reduced. Okay, so here's something very important. Okay, it computes a reduced Grosvenor basis for the ideal. So not only is it just going to give you, it's not going to give you the Grosvenor basis that our algorithm would have put out, but it's going to give you what's called a reduced Grosvenor basis, which is, I guess so not all Grosvenor bases are unique, but once you have Grosvenor bases, then you can kind of modify them a little bit to get a thing called a reduced Grosvenor basis, and I'll say what that is in a second. Okay. Anyway, this is what it returns here. And then if you really want to dig into it, if you tap a double question mark, right, what it'll give you is it gives you the source code, right, about what it's using. So if you ever need to actually dig in and see what an algorithm does in Sage, you can figure. I mean, you can just do it on command line, right, and it'll tell you what the algorithm is. That's pretty convenient. Okay, so let me just kind of suppress this. Okay, but anyway, so maybe I could leave a remark. Oh, I didn't want to do that. Okay, let me just leave a comment here for you guys. So there's tab completion. So you just double tap tab, then if you one question mark, a function gives you the documentation. And then two question marks, a function / method gives you the source code. Okay. All right. Another useful functionality is you can take so you can do polynomial. You can get the remainder by doing this, right? So after you have the particular basis, you can reduce, and then it'll give you the remainder. So what I did is I took this polynomial here, and then we're going to reduce modulo this ideal. So I guess one thing that we could do as a sanity check, right, is to see that the basis that we had will give you the same basis that they output there. So what did we have so far? So we had this, and then we had x times y xz minus y squared, and then we had another one, right? What was the other one? G3 was xy minus z, x times y minus z. Okay, so as a sanity check, this should return the same thing that was up here. See? This is the same thing as this. And this is what we had already computed. We already computed this bit. Okay? And so, all right. So this is a way that if you get into a long Grosvenor basis computation and you want to see what, you want to use a computer to check what you're doing, this is a way to do it. Okay, so let me say a little bit about reduced Grosvenor bases. Oh, let's see. Should I do a magic show right now? Okay, so let me give you another example of an application of Grosvenor bases. Okay, so this is the elimination theory one. Okay, so let's do R, X, Y. So we'll do T here like this. And then what I'm going to do is I'm going to make a new ideal. Okay, I'm going to do, okay, so this is an elimination theory example. Okay, So I'm gonna show you now, and then we'll maybe do this on paper a little bit too, paper. But what I'm gonna do is I'm gonna do the graph of this. Okay, so what I'm gonna do is I'm gonna do t minus x squared, t minus x. Let's see, sorry. Let's do it, x minus t, y minus t squared, and z minus t cubed. Okay, so what this ideal is this is the graph of the function. You know, like, you know, y is equal to mx plus b or whatever, right? But except for we have x is equal to t, y is equal to t squared, and z is equal to t. So you remember the rational normal curve? It's the image of t squared and t, you know, the t squared t cubed function. Okay. Well, if I were to look in variables x, y, z, and t, right? Then, and I was just going to set like x is equal to t, y is equal to t squared, z is equal to t cubed. What this does is this cuts out the graph of the function. Okay. And what we can do is we can take a Grosvenor basis for this graph, right? And what'll end up happening is that is you'll get some stuff, and notice that there's ones with t here. And I want to point out something to you, is that if you just kind of take all the things without t, right? And I just look at the later terms here, what is that? So does that look familiar to you? It's the same thing we got when we did this. Okay, and so what this computation does is it allows us to compute images of maps. So this is what's called elimination theory, right? What we've done is I've made an ordering. So I've done the graph of a function. So this is the graph of phi of t, which is t squared, t cubed. Okay, so this is a subset of A4, right? Okay, and what this does is so this ordering here, so the ordering here needs to be, the ordering is so that t is bigger than x is bigger than y is bigger than z. But the variable that we want to eliminate is first. Okay, and so if you compute a Grosvenor basis like this, and then you take all the stuff, right? If I intersect this with so this thing here, so this is the intersection of the basis with the ring k of x, y, z, right? And so this computes. So this thing computes the closure. This is a Grosvenor basis for the image of the map phi. Okay, and what it does is it essentially eliminated the variable t. Okay, so this is one way that Grosvenor bases allow you to kind of construct images. And so it turns out that this is the exact same thing as this. So this is the image here. So this x squared minus y, x cubed minus z. So that ideal actually does generate the image of that map. So that answered one of our original questions. Okay, so let me go back to some things on paper. I need to say what a reduced Grosvenor basis is, and I need to say what elimination theory is. Okay, so let me go back here. All right, it should steal the screen, I think. All right. Here we go. Okay, so let me just go back and point out what we just did. Okay, so this elimination theory thing, where was our original problem? Okay. So the question we had, right, is, so the question was here, what are the equations of this curve? And here was the map phi that we wrote down. So this is what I was writing down as phi, right? And so the equations, the answer to this question here, so the answer is that you take I, well, you eliminate, you write down the graph. The graph here. So we have x is equal to t, y is equal to t squared, z is equal to t cubed. So this is really, this corresponds to the ideal, right? X minus t, y minus t squared, z minus t cubed. And this is an ideal in many variables. So f of x, y, z, t, right? And then you eliminate, then you compute what this is. You compute x minus t, y minus t, z minus t, intersect f of x, y, z. Okay, sorry, z minus t squared, t cubed. Okay, and so this, what this does is it looks for everything in the ideal. Let's maybe not use black, because black we already used. So this looks for everything in the ideal. In the ideal, not in T. Not in, well, in, without T's, let's see. T's. Okay, and then the procedure for doing this was that we compute a Grosvenor basis, right, where T is the leading, is the first term in the ordering, and then and it turns out that if you compute the Grosvenor basis for this original ideal, and then intersect it with the lower variables, right? Then that's a Grosvenor basis for that ideal. So it's like the Grosvenor basis of the intersection is the intersection of the Grosvenor basis, right? So the motto here of the intersection is the intersection of the Grosvenor basis. So, you know, G intersect K of X, Y, Z. This is a Grosvenor basis for I intersect, or I said origin K, F. Where this thing here, this is a Grosvenor basis for I in f of t, x, y, z. Okay, so this is the motto. And that's kind of, that's the main crux of elimination theory, is to compute this. And then maybe I'll draw a picture here, right? So the idea here is that, you know, you have, so you have like the T line. So this is the T line. And then you can always factor it through the graph. So here's the graph. And so this is the coordinates x, y, z. This is gamma of phi. So this is the graph of the function phi. So this has x, y, z is equal to phi of t, right? So this is the t line, and this is the x, y, z axis. And then you can project down. So this is a projection. onto XYZ hyperplane. Right? Or, the t is equal to 0, right? And then this will be so you'll get something here. And you'll get something here. Right? And so this is the image of phi, right? And so there's this map here that goes from this into the graph, and then you project down, and then this would be the same thing as just taking phi. I don't know if this is helpful or not, but I'm just saying that every map factors through its graph, and if you eliminate variables, that's the same thing as a projection map, right? So this whole process of eliminating is projection. All right, so next time I said I would say what reduced Grosvenor bases are. So I just need to do some odds and ends, reduced Grosvenor bases, and then I want to talk a little bit about the Hilbert basis theorem, which will say some things about the proofs of some of these things. Okay, it will give you the idea of the proofs. All right, so I will be here for some questions if you guys have some. All right, thanks for listening.
Thanks.
Thanks, Taylor.
Thank you.